the class. First, we should start the discussion with PLL. So, as it has been already shared with you people all the necessary videos. I think most of you already gone through those videos at least once. So, hoping that. So, we have this phase locked loop, which is abbreviated as PLL. It's one of the very important and having a lot very important application in communication networks. Uh, as we know that okay, it has got the three important blocks. So one of the block is phase detector, phase detector. Next, I have a loop filter. So this is a loop filter. Then I have the feedback part. I have a voltage controlled oscillator, which we usually write it as VCO. This is error signal. Let me call this as some VD output. So let me call this as some V0, and this is the input voltage which you are getting. So let me say it as VCO itself. Otherwise, okay, this is the buffer. Okay, this is so as the name itself indicates. Can somebody be with me so that I can talk to him or her? Who is 32? 32. Can I get 32 unmuted? Hello. Is 32 there? Am I audible? Hello. Come on. 42? At least two? No one is there. Okay, who will volunteer? Okay, 10 marks for T1. Only if I offer something, it will come. Okay, this is for 10 marks for T1. Who will join me? Who is this? Who is this? Okay, fine. Uh, as you can see here, there are this is a phase detector. Phase detector is one which will actually compare the phase of VCO and the input voltage actually, what happens here is that if the phase of the input signal and the VCO signal are same, the output voltage of this phase detector is zero. If there is any difference in the phase of the two signals, then it will give an appropriate signal. It will give an appropriate signal. So it can be, of course, the phase detector output can be zero or it can be non-zero value. Actually, this phase detector is a mixer circuit. So let me say this is a mixer circuit. Mixer circuit is one. So as we know that okay, what do you actually mean by mixer? Which actually mixes the signal? So what do you mean by mixing of a signal in electronics? So suppose if you have a signal V1 and V2, so they will going to have, suppose assume that this is Vx cos omega 1t and this is equal to Vy cos omega 2t. These two are the signals which are having some magnitude Vx and there is a frequency omega 1 and there is a magnitude of Vy and there is a frequency of omega 2. These are the two signals, they will be get mixed. So this mixer is nothing but a circuit which is made out of transistors whose output voltage will be, of course, it's a nonlinear circuit. It's a nonlinear circuit. What does actually it will have is it will actually have the signal as it is, that is, it will have Vx cos omega 1t plus Vy cos omega 2t, so the same signals, and it will have its addition and subtractions. So it will going to have, of course, let me say it as Vz cos omega 1 plus or minus omega 2t. See here, I have the original signals as it is. I will have their harmonics also. When I say harmonics, it is Vx cos 2 omega 1t plus Vy cos omega 2 omega. You can see it's the second harmonic, it is a fundamental signal, and you can see there is a what? Addition and subtraction. Addition and subtractions are also happening. So now, so suppose assume that if the frequency of two signals, omega 1 and omega 2 are 100% same. So do we end up with signal components? Okay, let us assume that this is 10 kilohertz, this is also 10 kilohertz. So what are the signal components I'm going to have in terms of frequency? Will I have it at 10K one, 10K another? Will I have it as 20K and there is a DC signal and I'm going to have it 20K and I'm going to have it 20K? As per this, so I'm just talking about only the frequency components. So if you can see here, if the signals are same, if the signals are same, at this point VD, I have all these frequency components. All these frequency components will be the input for your loop filter. Loop filter is nothing but a low pass filter. This is a low pass filter. Why it is called as loop filter is it is there in the loop. So this is my loop. So that's why it is called as loop filter. So let me just remind this we are in LMRF. So don't be get confused. Okay, we are talking about loop means you are there in CSC. Fine. So we are calling this as loop filter because this is there in the loop of a network, loop of a PLL circuit. So when you have a low pass filter, does the low pass filter has got a frequency response something like this? Something like this. So will it have some frequency, cutoff frequency FC? Usually the low pass cutoff frequency will not be too high. Will not be too high. Meaning, no, this will be in terms of few hertz. This will be in terms of few hertz. So maybe few hundreds of hertz. If few hertz means okay, it may be 100 hertz, it may be 1 kilohertz, it may be 300, 400, 500 hertz. It will not be very high. So for such a low pass filter, having a cutoff frequency in terms of hundreds of hertz, does this pass through that? This won't pass through, this won't pass through, only this will pass through, this won't pass through, this won't pass through. You can see these signals won't pass through this. So I have only DC. I have only DC signal. So even though it is simply written that there is a single line coming here, but internally the circuit will be made such that whenever you have a DC output here, whenever you have one of the component is DC output, the error signal what you get is zero. What will be error signal zero? There is no correction required for this VCO to change the frequency so that it can track it. So we'll just come to that later. As long as the frequency of this and this is same, I will have a DC output along with other frequencies, whereas other frequencies fall in the stop band of this low pass filter. You'll be getting a DC. Effectively, I'll get a error voltage of zero. This error volt, this error voltage of zero will not change the VCO frequency. Meaning, maybe in your triple five timer, whenever your external voltage is equal to two-thirds of VCC, whatever frequency that you have designed, will it be operating at this frequency only? No, assume that if this is two-thirds VCC, this is two-thirds VCC, over and above that, if you apply some error signal. So can you see if the error signal is more than two-thirds VCC, will the frequency reduce in case of triple five timer? So if it goes below two-thirds VCC, will it increase the frequency? So I'm just referring to triple five timer. Can you see over and above that reference voltage, is the frequency changing? Suppose if the voltage is at two-third VCC, is the frequency as in the previous case? Meaning here on the same lines, if the error voltage is zero, the VCO frequency will continue to operate at a frequency of omega naught, meaning there is no correction required because these are matched. Now assume that this is the incoming frequency. I don't have any control over the incoming frequency. I can't say that okay, incoming frequency should be only this frequency. Incoming frequency can be because it's coming from an external source. External source can vary its frequency. Assume that its frequency omega, this was omega naught. Let us assume that this is omega naught. So we were taking it as okay, omega and omega. Let us consider this as V in. This is of VCO. So assume that this has become 11 kilohertz and this is now 10k, or maybe make it so and so. So now can you see here these frequencies? Will it end up with again one there is 10k, one there is 11k, there is one 22k is there, sorry 21k, and there is a 1k, and there is a 22k, and there is a 20k. See, out of all these, there is one frequency component which is at a low frequency. It will now pass through this. It will now pass through this. See, now this is other than zero, other than DC. So what will happen to this is, since the voltage is a non-zero value, the frequency of this VCO will not be 10 kilohertz. So what will happen? This was 11k, this was 10k, there was some error signal, assume that this was VE dash, which is a non-zero value, which is a non-zero value. This VE dash will make the VCO frequency to change. This may make it 10.2 kilohertz. So will you still have error signal? You will still have error signal because this component might have become 800 hertz. Now this will further change its frequency to maybe 10.5 kilohertz. This will happen in number of iterations because you are there in the loop. So then this will become 10.5. The error signal reduces. When error signal reduces, the amount of correction will also reduce. This is still 11k. This may become 10.8. Ultimately, it may become 11k. This is 11k. Then we say they are perfectly locked. So the intention or how long this looping will continue is as long as your error voltage is zero. Now, can you see here? Is the error voltage is keep changing? Suppose assume that error voltage is zero. If the error voltage is zero, what does it mean? They are matched. There's no issue. Suppose if your error voltage increases, if your error voltage reduces, what does it mean? The frequency or the frequency of this is different from this, and frequency of this, okay, over here. Here omega 1 may be greater than omega 2. Here omega 1 may be less than omega 2. Because I can have plus or minus, no? Either of can be maximum, either of can be minimum. Of course, here we just consider this as increase. It may also happen that this may become 8k, this is 10k. Then in such case, this will become 9.8, then it will become 9.5, then it will become 9, then it is 8.5, and ultimately this will become 8k. As long as this is not 8k, this will be keep on tracking. This is keep on tracking because it has to lock. It has to lock. So now this is the entire process that is happening. So as we can see here, so what is the role of each and every component is, because this loop filter will going to have some R and C, because when you have a low pass filter means this will always have a resistor and capacitor. So which is there seen in your IC also. 565 is an IC number which is very prominently used PLL IC. This is a PLL IC 565 which utilizes R and C, of course, for your loop filter. Okay, whatever the number. Uh, User can specify the VCO frequency because I can say, okay, what is my VCO frequency? You might have also saw that when we are define whenever we are defining triple fire timer, it is also called as a free running oscillator. This is free running. So whatever omega naught we are saying, this is a free running frequency. So what is free running frequency means? Whenever you don't have this one, this will be running at a frequency of omega naught, which we call it as free running frequency. This free running frequency will keep changing depending on your error signal. Error signal you'll get it depending on how much is the difference in phase detector. You can see here during this process of change of from 10K to 11K, can you see the error voltage whatever you have here? This detector output voltage, will it be keep changing like this? Because sometimes it increases, sometimes it decreases. So when something like this passes through this low pass filter, because this is usually at a high frequency, these ripples, these ripples are at high frequency, and when it assume that this is your high frequency signal, when it passes through a low pass filter, these ripple will be removed. What you'll get finally is an error voltage, which is something like this. This is the error voltage, this is VD. Because this is a low pass filter having something like this type frequency response, this is fine. This is fine because of the low frequency, whereas these ripples are happening at high frequency, they will be get smoothened. They'll be get smoothened. So what does this actually indicate? This will indicate, does this indicate this is how your input frequency is changing? Input signal frequency, whatever you have, there is a variation in the frequency of your incoming signal. Uh, of course, if you can see here, uh, there are two important terms to be defined here. One we call it as capture range, other is called as lock range. Uh, Now it is capture and lock range is something analogous to making you first to make you attend the class. So I need to capture your attention. So if it is interesting, you will be locked to my class. Otherwise, you'll go out. Correct? It's very important that I should first capture you people. So maybe in the beginning, I just ask everybody to join. And how long you'll be there with me, as long as the topic is interesting or you are interested in the topic. So both are true. Trapping will be interesting, but you're not interested. Okay, then you'll just lock out of that. Here the point in case of PLL is first I should capture the signal and I should be keep locked to it. Keep locked to it. So what is this capture range and lock range is? I think in the videos it has been explained. Let me just repeat that. Assume that your free running frequency F naught is at a frequency of around 50 kilohertz. 50 kilohertz. If the this is your VCO frequency, because VCO frequency you have a control, you don't have a control on the incoming frequency. Assume that you have a PLL, with a free running frequency of 50 kilohertz. Assume that you have the input signal which is at 500k. 500k. Now it is like too far, so I cannot able to capture this signal to track its variation. So it is out of my capture. Why it is out of my capture is because my loop filter cannot able to generate a frequency such that its frequency can go up to 500 kilohertz. I don't have such a larger error signal so that I can able to change this frequency so that this will become 500k. So this is not in the vicinity of capturing the signal so that I can track it. Because the whole idea is this is an input signal whose frequencies keep on changing, keep on changing. When the frequencies keep on changing, I want to find out how the frequencies keep on changing. I don't know whether in your analog communication, I think you might have been taught about amplitude modulation. What is there in amplitude modulation? How do you define amplitude modulation? Much more clear definition of amplitude modulation. Anybody for 5 marks answer in analog communication in LMRS? What do you mean by come? Okay, much more clearer. Of course, I could able to get your conceptual things, but much more clear definition of amplitude modulated waveform. Mm, mm, mm. Okay, that's fine. Any one more answer? Hello, one more answer. Okay, instantaneous. Okay, fine. Okay, of course you can all the definitions are fine. Suppose if you just slightly fine tune it and say it, the variation in amplitude of a high frequency carrier signal in accordance with the instantaneous value of the modulating signal is called as amplitude modulation. Now you are changing the amplitude of high frequency carrier signal. How you are changing? You are changing in accordance with the instantaneous value of the message signal. Instantaneous means at that instant, whatever is the amplitude of your message signal, that should be reflecting in the amplitude of your carrier signal. Can you see that there is you are actually if you see the amplitude modulated waveform, its amplitude represents the variation of your message signal. Can you see the envelope there? Envelope is actually your message signal. That is amplitude modulation. So I have been also talked about frequency modulation. What is that? Perfect. Now can you see there? You have, of course, is it easy to detect the amplitude change? What are the major advantage of your amplitude modulation? What are the major advantage? Major advantage of amplitude modulation is its detection is the easiest one. You simply have an envelope detector, you can detect the envelope, correct? But in case of FM, it's a bit difficult. Why? The amplitude is constant. You need to now keep track of the frequency of the carrier signal. Can you see is this PLL useful in tracking the change in the frequency so that you can get the error signal? That error signal is equal to your message signal. So one of the major advantage of PLL is demodulation of FM signal. Because if I write if, if if I write the modulating signal here like this and then the carrier frequency, now you can see carrier frequency is very high here and it is low here and it is something like this. See here the frequency is high, the frequency is the low. If I can able to track this variation in frequency, so which can be detected in your phase detector, does your error signal replicate this? Can you see there is a change in the frequency? Does the error signal is more? Does the frequency change? Does the error signal reduce? Suppose if you don't have any modulation, suppose if this is equal to your VCO frequency is equal to F in, what is the output now? You will have a constant voltage, no modulation. There is no modulation. Suppose if you modulate this signal using a modulating signal, which yields this type of variation frequency, can you able to detect it using a PLL which is actually varying the frequency? The error signal will represent your modulating signal. So this whatever VE you have. So this is actually the error signal which is proportional to the variation in the frequency. We will take this as the output of your PLL as the demodulated output. Demodulated output. Correct? So now assume that the VCO frequency is 50K, the input frequency is 500K. Can I able to capture it? I'm unable to capture it is too far away. So I need to just make sure that this should be in the vicinity, maybe 55 kilohertz. If your incoming frequency is 55 kilohertz and if the freeing frequency is 50 kilohertz, it can able to capture that so that it can track it. At the time of capturing, it has been captured. Once it get captured, even if the frequency go to 75 kilohertz or 80 kilohertz, if your VCO and phase detectors are having good sensitivity, it can still lock to this frequency. Both are changing. Suppose assume that if the change in your incoming frequency is too high, if it goes beyond 100 kilohertz, then it was keep holding it. It was keep holding, but the increment is so high that it cannot cope up with that. Then it unlocks. Then it unlocks. When it unlocks, the frequency of VCO goes back to its free frequency of 50 kilohertz. 50 kilohertz. So what I mean to say is, you have, suppose if I write this as my frequency axis, this is running at a frequency f naught. This is running at a frequency f naught. There is a certain range of frequency around f naught where I can able to capture my signal. So this I call it as range. Capture range. Once I capture it, assume that incoming frequency, okay, VCO frequency is 50K, incoming frequency is 52K. Has it captured? Assume that this is around 60 kilohertz. Assume that this is 40 kilohertz, meaning around 50 kilohertz. If it is less by 10 kilohertz or greater by 10 kilohertz, I can able to capture the signal. Once it gets captured, upon capturing, even if the frequency goes to 80 kilohertz, assume that 80 kilohertz, till 80 kilohertz, it locks it. If the incoming frequency goes above 80 kilohertz, it unlocks. It can't go beyond that. And over here, let me just take this as 20 kilohertz. So this range, I call it as lock range. Up to which it can lock. What do you mean by lock? VCO frequency will be keep tracking the incoming frequency if it is in lock range. So what is this capture range? It can first capture it. So first, because unless you people attend my class, I can't capture attention. I cannot just, okay, you cannot just hang on to my classes. Only when you come to my class, I can say that, okay, these are the things, okay, you can be get interested. If you are not there in the class, okay, how do I create the interest? The point here is that I have to first bring you into the class. Once you are there into the class, I can extend my class. If I extend my class too much, you just go out. It's almost analogous to that. See here? First, we're going to have a capture range. It is around the free running frequency. Once I get capture, if it is interesting, I can extend the class till this point. If I go beyond that, okay, you people think it is too much, it will go out. No, I'm just giving an analogy. It is the same thing on the other side also. On the other side also. So I can ask you to come bit early, something like that. So this is just okay. May not be realistic in your classes, but here this is fine. So first it is capture range is always lesser compared to the lock range. So lock range, okay, once you get captured it, you can extend that frequency up to which you can hang on to that frequency variation will be quite large, so on. So this lock range and capture range purely depend on the loop filter time constant and the sensitivity of this VC1 phase detector. Because if this VCO cannot change its frequency to a greater extent, then your lock range is limited. Suppose if it cannot give what difference voltage to a greater extent, then it has got limitation. And of course, this is purely deciding what is the capture range. Capture range. Of course, all of the three will decide what is the lock range of your PLL. So, of course, this is as I just explained here. Any incoming FM signal has to first, if it has to demodulate, first it should come into the capture range. Once it comes inside the capture range, then you can just extend the frequency beyond some extent so that you can able to get a demodulated waveform. Get the demodulated waveform. So we have three important things: free ending frequency, capture range, lock range, error signal, loop filter, and we have something called as loop filter time constant, because this is time constant. If time constant, if RC is too large, if RC is too large means what? If it takes longer time to capture the signal, which is not good. It should quickly capture it. It should quickly capture. Suppose if RC is too much, what does it mean? Frequency is less, no? Suppose if RC time constant is too much, frequency is less, meaning that it has got very limited capturing. So that is not good. RC should be quite less, meaning uh, it should not take too much time to capture it. The loop filter should not take too much time to, or the entire PLA should not take too much time to capture the thing. If RC is too less, then what is your F? F is actually equal to 1 over 2 pi RC. If this is less, is your cutoff frequency more? So it is better. Of course, it will what capture even the largest variation. It will capture the largest variation. So these things we will going to see in your remote lab. As I change the value of RC, if the RC value reduces, I can have a larger lock range and capture ranges. Of course, we have the option that in the remote lab, so where you can able to change the time constant of this, and you can see the change in the lock and capture range. Because when I say lock and capture range, this range can be extended or this range can be truncated depending on the RC time constant. I hope okay that what I planned for that PLL. So now let us move on to. I think that completes how many unit? One unit, huh? Yeah, one unit is over now. Of course, it took long time. And of course, this ADC DACs will move fast. So we have next topic called as digital to analog converter. Uh, I think all of you heard about this buzzword IoT. What does this IoT stand for? Okay, can somebody come in now for another 10 minutes? Okay, Subramanya, you are guaranteed with T1 plus 10. Okay, I don't know when does this T1 will happen. When it is scheduled? As per schedule, okay, when is T1 should of this month? Okay, fine. So this is for LMRF. Uh, who is uh, who is the next person to come for T1 plus 5 marks? Because I don't have too much time now. Another 20 minutes plus 5 marks for same LMRF. Any volunteer? Hello, who is this? Vinod. Vilas. Okay, fine. So this was Subramanya. This is now Vilas. Okay, this is a proof that okay, I have to give few marks. Okay, heard of this IoT? What is IoT? Okay, what is that actually meaning of Internet of Things? Can you just slightly elaborate? Coming. Okay, okay. It's connected. Then what? Connected for what? Assume that now you're sitting at home. Now you're sitting at at your home. You'll be asked to control a remote lab. So is it something like IoT there? You're controlling something, correct? Suppose if you are asked to control the fan at a place. Assume that you are there, okay, outside. If you want to control the fan to increase the speed or reduce the speed, is it possible to do that depending on the temperature, or can you make it automated? How it is possible? Okay, perfect. Okay, what is this IoT? Okay, what is this? Okay, IoT based devices are connected to it. What does what does it should have? Because Mhm. What signal? Because you of course, so maybe in the last semester you might have done in your AAC lab. So you are actually controlling that fan, no? So fan was switching on or switching off depending on some temperature. If the temperature exceeds 35 degree, then you are making your relay to switch off. That is only switch on, switch off. You can actually able to change the speed also. What was actually happening there? Uh, where was digital signal? Where was analog? What was analog? What was digital signal? Okay, you have a physical parameter in the form of temperature, correct? Were you getting that physical temperature which was there in the form of a physical parameter? Was it converted to voltage using LM35? Was that LM35, was it a analog voltage or digital? Was that analog? So how did you actually read that inside your what did you actually do with that analog signal? Where did you actually give it? You actually read it in Arduino, correct? What was actually Arduino doing? Was it understanding 300 milliwatt, 200 milliwatt? Was it understanding? No. You have Arduino which only understands zeros and ones, correct? But you have an analog voltage from a triple five timer, which is an analog voltage, maybe 300 millivolt, 400 millivolt, depending on the temperature. How does your Arduino was trying to understand these analog voltages? Can it understand 300, 400 millivolt, or because it needs a digital value? Nine. What I have is, so this is what you had, no? This is LM35. So you had a ground, of course, you have a VCC, and then you have a V0 here. This was actually connected to what? Arduino. This will handle zeros and ones, correct? What was there here? This is analog signal. This is like, okay, in terms of millivolt, or it can be in terms of volts. But this knows only zeros and ones. This, how do you convert this millivolt and volt to zeros and ones? So you need to have an analog to digital converter, correct? So you have an analog to digital converter, and then assume that you have a fan here, you have a fan, you have a fan here. This again requires analog voltage to change the speed. It's not okay turning on, turning off. This is what? This is ADC, correct? So assume that I want to change the speed to speed 1, speed 2, speed 3. For speed 1, I want to have an analog voltage V1, I want to have it as V2, I want to have it as V3. Correct? So for a assume that for 300 millivolt, for 350 millivolt, and for 400 millivolt. So does these corresponds to temperature of 30 degree, 35 degree, 40 degree? If I'm correct. This is temperature degree centigrade. This is okay V naught of your ADC. And what should be the speed of your fan? Fan speed, let it be 1200 RPM. Let this be 1500 RPM, and let this be 2000 RPM. Correct? Because as temperature increases, does the speed of your motor should also increase? The speed of your fan should also increase. Now, for that, does the voltage required for this fan, does it require A1 amplitude, A2 amplitude, A3 amplitude? Because unless you change the amplitude, the speed will not change. Am I correct? So it was not simply turning on, turning off of your fan. It is changing the changing the speed of the fan depending on the temperature. Correct? Now you have a physical parameter. Correct? You have one more physical parameter. Am I correct? This is temperature. This is speed. Am I correct? Are these two are two physical parameters? In between that, I have an Arduino. Correct? This handles only zeros and ones. On this side, I have analog voltage. On this side, I have still analog voltage. Am I correct? So this analog need to be converted to digital. Do you have a ADC here? So this digital need to be again converted to analog. I need to have a DAC. Are you getting now? In this microcontroller, which needs zeros and ones for manipulation, the input physical signal is taken inside as a digital parameter through analog to digital converter. Whatever manipulation that you have done here, so what you're doing here, if it is so and so, you make a speed of 1200. For that, you have a corresponding analog voltage. So whatever digital equivalent you have has been converted to analog here. Whatever digital equivalent for a speed of 1500 has been converted, and you are having it as A2. Can you see there is a digital signal has been converted to analog? So for any control of physical parameter to control the other physical parameter, you need to have this ADC and DACs are a must if at all if you want to interface that to any digital controller. If you have any microcontroller, if you want to control any physical parameter, you need to have one ADC to convert analog to digital, and using digital you can handle the parameters very efficiently in your controllers. You do the manipulation using digital values, and if you want to again give the analog output to your external world, you use a DAC, that is digital to analog converter, so that these analog voltage can able to change the physical parameter that is there on the actuator side. So sensor is a physical parameter, actuator is a signal, same parameter. It gives analog voltage. This requires analog voltage, and since it requires digital, you need to have a to D converter. Since it requires analog voltage, you need to have a digital to analog converter. Digital to analog converter. So in this LMRF, we'll be looking at ADC as well as DAC, as well as DAC. So first we will start with this DAC, that is digital to analog converters. Digital to analog converters. Is that fine? Any doubt here? So the purpose of having DAC is to convert digital to analog output. Digital to analog output. So, shall we say this DAC is, suppose you want to represent that DAC by a simple block diagram. If I say this is digital to analog converter, will it have n number of inputs and a single output? Correct? So, will it have, if I say this is for B1, B2, B3, dash, 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 Bn. These are the binary inputs. When I say digital, it is in binary nature. So you have binary inputs and you have a output V0. You have output V0. So since it has to operate with some voltage, we will have a V reference. We'll have a V reference voltage. So DAC basically consists of n number of digital inputs and a single analog output. And of course, we want to have a reference voltage Vref. Vref. So I can write the expression for this V0 as equal to some gain times V reference multiplied by digital input DI. DI. So this is a digital input. Output is nothing but some gain multiplied by reference multiplied by digital equivalent input. So what is this DI can be? DI can be equal to, because whenever you're writing these what digital values, they are always put in binaries. They are always put in binaries. So I will write it as B1 2 power minus 1 plus B2 2 power minus 3, goes on like that. It is Bn n 2 power, sorry, this is minus 2, minus 1, minus 2, minus. So you just questioning what is this? Why it is minus 1? Why it is minus 2? Why it is to the power minus n? So let us try to understand why it is so. Suppose you have 3-bit binary number. Will I just write it as a B1, B2, B3? This is a 3-bit number, 3-bit binary number. So let me call this as MSB. Of course, this is LSB. What is the value of LSB, or what is the value of MSB? Is it actually 2 power minus 1? This is 2 power minus 3. This is 2 power minus 2. Meaning, what are the how many possible values does this can have? So this can have 8 numbers. This is 0, 0, 0. Then this is 1, 0, 0, 0, 1, 0, 1, 1, 0, 1, 0, 0, 1, 0, 1, 1, 1, 0, 0, sorry, 1, 1, 1, 20. Correct? So what we do now is, uh, so what is di now? So instead of writing all these values, what I do is di is equal to b1 2 power minus 1 plus b2 2 power minus 2 plus b3 2 power minus 3. So what is the value of this one? This is b1 by 2. This is b2 by 4 plus b3 by 8. Correct? Correct? So is this your B1, B2, B3? So this B1, B2, B3 can be either 0 or 1. Correct? Because this B1, B2, B3 can either take a value of 0 or value of 1. Suppose if it is 1, 1, 1, if it is 1, 1, 1, what is the value you're going to have? What is the value you're going to have? Is it half plus 1 by 4 plus 1 by 8 for 1, 1, 1? Correct? Is it 7 by 8 I'm going to get? Correct? So this is when it is 1, 1, 1. So this is B1, B2, B3. So this is your DI. What is your DI if it is 0, 0, 1? Is it actually 1 by 8? What is when it is 0, 0, 0? Is it 0? What is if it is 1, 0, 0? Is it half? Now, meaning the output voltage V naught is K times V reference multiplied by B1 2 power minus 1 plus B2 2 power minus 2 plus B3 2 power minus 3, keep on going up to Bn 2 power minus n. So what are the possible values of one B1 B2 or B1 any binary bit? It is 0 or 1. 0 or 1. Correct? So if you have three bits, how many possible V naughts you want to have? If B's are 3 bits, then V naught is equal to actually how many values? You'll have 8 possible values. That is 0 plus 7. Am I correct? If you can see here, this is 0, 1, 2, 3, 4. Okay, this is including 0, 1, 2, 3, 4, 5, 6, 7, 8. Correct? If it is 4 bits, it is 16, which is nothing but 0 plus 15. If it is 8 bit, what is 2 power 8? 256, including 0, 255 different possible combinations. Correct? Now let us try to see. Let me just write. Okay, you have a graph now. No? Okay, we'll just see these things uh, in more detail. So, what are all these voltages? What are these different values, and what is the error that may occur in your DAC, and how do we analyze, and what are the circuits which can convert this digital to analog values? We will show those things in coming classes. Okay, then, thank you.